So, in this session we will be discussing about the mechanical operation. This is the beginning class of mechanical operation, and the first topic is agitation and mixing of liquids. So, it is agitation and mixing of liquids. See, what is agitation? Agitation is basically when the process when we induce a motion in a material, and generally that motion is a circulatory type, and we do this induce this motion in a mixing tank, right, some sort of device like that. And the purpose of agitation is basically, there may be different purposes of agitation. It may be heat transfer, it may be mixing itself, right. Whereas mixing is distributing one material or one phase into another phase which were initially separated. The one to another phase into one another. That mixing may not produce a solution. It may produce a liquid-liquid dispersion, a gas-liquid mixture, a solid mixtures like that. So, in a sense, agitation is inducing motion in a material generally a circular motion is induced in a material kept in a container, right. That is basically agitation. Whereas mixing, on the other hand, is distribution or distributing two or more initially separate phases. Okay. Now, the purpose of agitation may be mixing, heat transfer, etc. Right. Now, you see a tank of liquid singly, right, can be agitated, but it cannot be mixed. Whereas you can mix a hot liquid and cold liquid in a container. So, let us discuss the purpose of agitation. First, it may be mixing two miscible liquids. Second, to produce a liquid-liquid dispersion. The example is mixer used in LLX, liquid-liquid extraction. 3, to produce a gas-liquid dispersion. to produce a solid liquid mixture for heat transfer, etc. So these are the major purposes of mixing. These promoting heat transfer and all. Okay. Now what is the agitation equipment we use? It is basically a cylindrical tank fitted with jacket, and most of the time the top is covered. Sometimes in some naive kind of application we can use open top. So here we have jackets. We have the circulation of cooling water. So this is the jacket, central axis, cooling water in, cooling water out. We have a pipe which is dipped inside. So this is the inlet pipe. We can have multiple numbers of inlet pipes like this if necessary. And we have an outlet here. But the most important part is the overhung shaft. The shaft that is along the vertical axis of this vessel and mounted from the top. And there are arrangements like gear trains may be there, and we have a motor. Speed reducing block and the shaft here fitted with impellers. So there are different types of impellers, we will discuss it. The shaft, impeller, and we can also have thermowell, for temperature measurements and all. So this is typically the agitation equipment, right? And you see the bottoms, this not a sharp corner at the bottom to break the stagnant zone of the liquid, and we can have baffles here. The purpose of using the baffles I will discuss. So it's basically to promote mixing. For the time being, just try to understand that it is the baffles are necessary to produce a good mixing process. An impeller is mounted on the overhang shaft, the shaft supported from above, the shaft is driven by a motor. Sometimes it is directly connected to that motor is directly connected to the shaft, but most of the time it is connected through a speed reducing device. Right. That's a gearbox and all. The inlet outlet lines, coils, jackets, wells for thermometer and other temperature measuring devices are also included. Now, what is the central part of this agitation and mixing? The impeller. So, we have to focus on the impeller itself. And we have to classify, understand the different types of this impeller and all. So, impeller, there are of two types. One is axial flow impeller, and another one is tangential or radial flow impeller. So, for this axial flow impeller, it produces axial current parallel to the shaft or shaft axis, produces radial current which is tangential or which is perpendicular to the shaft axis. Right. The example of this axial flow impeller, tangential or radial flow impellers, most of the turbine, or rather it is a straight blade turbine, and here it is the propeller. Right. So, we have to distinguish between these two types, and let us first focus on the propeller. What are propellers? So, these are high speed propellers. Let us write the characteristics. High speed axial flow impellers. Right. So, the flow pattern in a propeller, you see, we have a tank if it is fitted with a propeller, and there is the liquid level in the tank. It produces strong axial current. So, this axial current gets reflected from the top and moves back following the area close to the wall, deflected by the base, and again comes here. So, this is the typical flow pattern of a propeller. Right. They are generally used for low viscosity liquids. So, this propeller is highly effective in breaking all stagnant zones in an agitator, or in an agitation tank or mixing tank. Right? So, whenever it revolves, it rotates. You see the system is something like this from the top view. So this is a typical example which is called as 3-blade marine propeller, generally used for marine transportation in the ships and all, but in much reduced size we use it here for mixing purpose. The diameter of the propeller, so here let me write diameter of the propeller rarely exceeds 18 inch even for larger tanks. Speed, it is 1150 to 1750 for high speed duty, (400 to 800 RPM). Sorry, this is RPM for low speed duty. Now, when the propeller rotates, what happens? It produces this axial current, right? And mostly it is oriented in such a way, so it produces, sucks the liquid, and it will be forming a kind of helix, right? Actually, it is a helix. So, from there, it deflects and actually it moves down and again comes back to that inlet of this propeller region. Now, whenever it is following a helical pattern, so propeller next generates helical path lines, right. So, now you see, when we think of an helix, it is like this, and the distance the liquid travel per unit rotation is called the pitch, and that is why we sometimes refer the pitch of the propeller as square pitch propeller. Square pitch means pitch is equal to the diameter, right. So, square pitch propeller, the ratio, actually the fixed distance depends on that angle of inclination. The ratio of the distance of the propeller to the diameter is known as pitch. So, this is not exactly pitch, we should write that pitch is equal to Pt divided by dA. dA is the diameter of the impeller. So, square pitch means Pt equal to dA, as you can obviously understand, is said to be square pitch if pitch is equal to 1, right. Now, in deep tanks, this diameter is much lower compared to that height. We can use multiple propellers mounted on the same shaft, right. They are mostly equispaced. So, you can mount the propeller at say here we may use multiple propellers for deep tanks. So, something like this, here, etc. Right. So, that is about the propeller. Next, it comes to the axial or this radial flow systems, radial flow impeller, and the slow speed radial flow impellers are called paddles. Paddles, slow speed radial flow impellers, commonly used for slow speed requirement in case of highly viscous fluid. Right. So paddles, it seems that it looks like this. See? It may be the two blade paddle. These are two blade paddle. We can use these four blade paddles as well. So this is the typical four blade paddle. Alternatively, for the churning over the entire tank, we can use this sort of paddles. The shape may be hemispherical as well, and this type of paddle is called anchor agitator. This looks like this anchor of the ship, right? So this is called anchor agitator, and it churns the liquid in a tank at a slow speed. The paddle dia is close to the diameter of the liquid. So for the simpler problem, an effective agitator consists of flat bed turning on a vertical shape. Two bladed, four bladed paddles are common. Sometimes the blades are pitched. Pitched means it is slightly slanted, right? But mostly we use vertical paddles. It's turned at slow at moderate speed in the center of the vessel. They push the liquid radially and tangentially with almost no vertical motion. The impeller, unless the blades are pitched. Whenever you pitch the blades, pitching means inclinations, that these blades will no longer be straight, they will be slightly inclined. So whenever they are inclined, they will produce an axial motion. Right. In some design, the blades conform to the shape of the dish or hemispherical vessel, so that they scrape the surface or pass over it with close clearance. The paddles of these kinds are anchor agitator. Here we have the vessel walls like this, right? So they can effectively churn the heavy viscous liquids. So the typical industrial paddle turns at 20 to 150 RPM. So 20 to 150 RPM is the standard speed range of the paddles. So next, we have the high speed radial flow impeller, that's called turbines. So let's see what are the turbines. High speed radial flow impellers made for wide applications in case of liquids with changing viscosity. Right. Wide range of viscosity and the flexibility in operation is there in case of turbines. So turbines, generally the typical examples are that open straight blade turbine or open turbine is what, say you have this shaft, there is a small extension, and here we have the blades. Right. So this is the typical open turbine. So you can have dish turbines. Dish turbines look like this. So why we are using the dish? Because the dish prevents all the possible axial flows. It prevents all possible axial flow, right? And these are called a 4-blade or 6-blade Rushton turbine. These turbines are often referred as Rushton turbines. However, here we may have axial flow, right? If the plates or turbine blades are not perfectly vertical. Now, if I intentionally want to generate this axial flow, we will use pitched blade turbine. Sorry. It's like this. This is here. So this sort of pitch blade turbines which can generate axial flow, this surface is not vertical, it is inclined, right? As you can see, so this will generate axial flow in addition to radial flow. Radial flow will obviously be generated, but in addition to that will generate axial flow. So radial and axial flow. Right, so these are called pitch blade turbines. So you see in a turbine the flow pattern for turbines. So which is purely radial. So you see that if I am using this sort of turbine which is purely radial, this is the liquid level. So here it produces the strong radial jet which deflects, which gets deflected by the wall, divides, and one part moves up, circulates back to the turbine itself. And another goes to the bottom and again moves up, circulates back to the turbine. So this is the flow path lines for turbines. It's purely radial turbines. Right. So, here turbines, this diameter of the impeller is smaller with the paddles, 30 to 50% of the diameter of the vessel. Generally, the diameter, turbine diameter is 30 to 50% of the vessel diameter. So, anything which I have missed, let me check out. So, here effective for very wide range of viscosity. I have told in low viscosity liquid, turbines generate strong currents that persists throughout this vessel, seeking out and destroying stagnant packets. It is obvious. Near the impeller, a zone of rapid current, high turbulence and intense shear is generated. The principal currents are radial and tangential. The radial currents includes, the tangential currents include this induced mixing and swirling, which tangential means in this direction, right, in circulatory direction, in the azimuthal direction. The basic flow pattern of the liquid in a standard turbine is shown. Now, you see that we have to justify that why we were using these baffles. In the diagram of these agitators, I have shown that we are using some strip, some this rectangular shaped strip, right, which has got very small thickness and its height is nearly equal to the height of the liquid pool in that tank, that we simply weld on the inner surface of the tank. So, these are called baffles. So, why you are using these baffles? So, that is to be justified. Right. So, you see what is the flow pattern. In order to understand or justify the use of baffles, the flow patterns in a cylindrical agitator, agitation tank. See, it is a cylindrical tank, and here we have, let us say, whatever it is, a propeller or a turbine. This turbine we have fitted, and this is the surface. So, if I fix our coordinate system here, this is z direction, this is r direction, and this is the theta direction. So, velocity field which is being produced, whatever be the type of the impeller, there will be three components. One is radial component, azimuthal component and axial component. So, this is radial, this is angular or azimuthal, and this is axial. Now, the pattern of motion which the shaft induces is circular or angular pattern, right. So, liquid, when the shaft this impeller cuts the liquid, it mostly will generate because of this drag in the liquid, the liquid actually imparts on the shear, this stirrer blade, right. So, that is basically a circulatory motion. So, primary feature or primary motion mode. So, here we have to note that motion is induced. So, motion is primarily induced in angular direction. Now, you think of a situation where we have entirely V theta, V is mostly V theta, right, and negligible VR and VZ. What will happen? If we have high angular velocity, there will be vortex formation. That is, if the liquid is, if the shaft is here, the liquid will assume a shape like this, right. So, average height is somewhere over here. So, what is being done? So, this part of the liquid is above the average height, right. And whatever energy you are giving to that system, major energy is used to maintain the distribution of height, right. So, this if it is h of r, so actually major energy is wasted to lift the liquid above and over this mean level of liquid, right. So, mixing in some way is impeded, okay. So, we have to note that from this understanding that VR and Vz favors mixing, whereas V theta induces stratification of liquids. What does it mean? It actually, V theta, if you have a high angular kinetic energy, that is V theta and V theta square is much higher than VR and Vz, what will happen? This will stratify the liquid, this is arrange the liquid in different layers, right, and these layers will not interact. Like we can think of a torus like shape here, where the liquid circulates without interacting with other similar shapes or liquids inside other similar shapes. So, that basically impedes and hinders the process of mixing, whereas if I have high V theta and high Vz, right, so then definitely the mixing is promoted. So, what we have to do? Recommendation is must be effectively converted to VR and Vz, right. So, primary angular motion which is induced by the shaft is to be majorly converted into VR, that is radial and this axial component. The tangential component should be reduced as much as possible. So, for that there are three specific engineering solutions to this problem, right. We have to eliminate the vortices and the vortex being formed, and we have to convert this increased V theta, which is because of the circulatory motion of this impeller, we have to convert it more to VR and Vz. So, there are three engineering solutions, right, used for this purpose, and the first one is called, is used of inclined or eccentric starter, right. What you are doing here? If this is the tank, you place the starter like this. So, this is inclined starter. Right. So, in use of inclined starter, mounting of the shaft itself is a problem. So, mounting the shaft in an inclined fashion is a problem, is problematic. Right. We can use eccentric starter as well. We place the starter here. So, this is the eccentric stirrer. We are not having the alignment here of the shaft axis with the central axis of the tank. We are placing the shaft or the impeller somewhere eccentric close to that, to one side, to one radial direction. It is close to the periphery. So here what may happen? Dead zone may form. So prone to dead zone formation, specifically towards the peripheral region. Right. So this problem can be solved if I use a draft tube. This simply partitions the flow domain into two, like if it is a propeller type impeller, we can put a tube here, it is called draft tube, and put the propeller here, right, somewhere inside the draft tube. So these two flow regimes, this is regime 1, this is regime 2, they are partitions, this regions rather. So these regions are partitions. So obviously this circulation, the continuity of this circulation is not, it's being hindered, and actually here the V theta and here inside and outside the V theta will be 0. So V theta continuity and the shearing in this theta direction is specifically, we are disrupting the continuity, and as a consequence we are converting this V theta more into VR and VZ, right, and promoting mixing. So draft tube, this is the draft tube for propeller, and alternatively we can also use a draft tube in case of turbine fitted tank. So here the drafting will be like this. Draft tubing will be like this. Again the continuity of this V theta is, so this is the draft tube. Right? And if in case of turbine, it should be placed below this bottom half of this draft tube. So this is the draft tube for turbine. Right. So what you can see here, that as we are breaking the continuity of this V theta, we can effectively convert this V theta more into this VR and VZ. But the problem is mounting of the draft tube. It must be symmetric, it must be centrally arranged, right? Otherwise there will be this non-optimal use of this energy which we are giving to that system. So the most easy solution to this problem is the use of baffles. What are the baffles? Here in a tank, this is the impeller. We use this sort of blades. These are baffles. Right. Now what will happen? See, in this region V theta is high, as V theta, it's a peripheral region, omega into I. Right. So if I have a baffle like this and a circulatory path line is hindered, so it will get reflected, either move in the VZ and it will move also in the VR. Right. So, a large circulatory path line which we may expect in case of unbaffled tank. Now, it will be hindered because of these baffles which are welded to the inner surface of the cylindrical tank, and it will hit there and it will be effectively converted to VR and VZ, right. So, that is the use of baffle. We can use multiple numbers of baffles, 6, 8, 4, etc. For smaller tanks, we go for 4 baffles. So, more importantly, we have a standard design for these turbine feeder tanks. So, this I am not asking you to remember that what should be my optimal shape ratios or shape factors. Shape factors are the dimensionless numbers. It is a geometric ratio, dimensionless number, right, like this height or the level of the liquid by the diameter of the tank, then position of the diameter of that impeller divided by the diameter of the tank, etc. So, standard design for turbine feeder tank is this. See, these are the baffles. Now, J we call the baffle thickness, though it is not geometrically the thickness, but the width of the baffle rather, but it is called baffle thickness. Tank diameter is dt, right. Height of the liquid is h. Impeller diameter is dA. Position of the impeller from the bottom, yeah, it's E. And this is L, this is W. This turbine blade length is L and its height is W. Now, what we have? The optimum shape factors. So, here we have this L by, first is dA by dt is 1/3, h by dt is 1, j by dt is 1/12, right. E by dA, E by dt is also this 1/3, right. Yeah. dA by dt 1/3, dA by dt is 1/3, h by dt 1, j by dt 1/12, v by dt is 1/3, w by dA is 1/4, yeah, and L by, this is 1/5, this L by dA is 1/4. So, these are the optimum shape factors which will for optimum or minimum power usage. So, power itself is pretty important, right. So, this is an outcome, how we are getting this, where from we are getting this. So, here this power consumption is in an agitator tank, that is the most important issue we have to discuss. So, power consumption in an agitation tank. Right. So, first the associated dimensionless numbers we must discuss. So, first one is flow number. In power calculation, these numbers play an important role. So, what is a flow number? You see, if I think of an agitator from a top view, this is the extension, this is the shaft, this is the turbine blade, right. Here we have a tangential velocity u2, which is omega into r2. Just like it's very similar to the centrifugal pump theory. So, this is r2 and here we have v2. Why we are using this sort of angle? It's moving in this direction. It should be vertical, but vertical is vertical direction of v2, the diverging liquid in the tangential flow. It's true if we have this perfect guidance assumption we have discussed in fluid mechanics. However, as we have a finite number of these blades like 4 or 6 or 8, right, there are no infinite number of blades with very small and infinitesimal thickness. So, basically there will be divergence from this perfect guidance direction. So, it is v2 is in this direction, and if we take a vector sum of this u2 and v2, we will get capital V2. This angle, the angle of this vane, is not exactly the vane angle, the effective angle in which it diverges, it is beta 2. So, this velocity component, if we resolve, is Vr2, this is Vu2, right, and this angle again is beta 2. So, you can understand that Q is equal to Vr2 into AP. What is AP then? If we think of this stirrer, the impeller, it is fitted with this sort of straight blade, let us say. This area, this angle, this is AP, right, area AP. So, Vr2 into AP. Now, Vr2 is what? Vr2 is u2 minus Vu2 into tan of beta 2 into AP, right. Yeah. Now, for similar, the similar means it is following this geometric and kinematic similarity. For similar agitators, Vu2 by u2 is equal to k, a constant. So, it is 1 minus, so yeah, it is 1 minus k into tan beta 2 into u2 into AP. Now, AP is equal to pi into dA into T. Now, T or here it is W, right, this is W, pi into dA into W, right, and from geometric similarity, W by dA is also a constant, so it is C. Just like here in the standard design we had W by dA is constant. So, Q is 1 minus k into tan of beta 2 into pi into dA into n, right, which is u2 into this pi into dA into CdA. So, what we can have, that q divided by n into dA cube, which we define as flow number n cube, is 1 minus k into tan beta 2 into this pi square into C, right, all constant. So this is the flow number. Flow number, it's actually this Q is what? Q is the flow rate which is diverging out of this area, right? The hatched area, whatever is diverging out is Q, right? And N dA square is what? It's proportional to that A volume displacement rate by the starter. So the physically the actual flow rate generated by the agitator or by the agitator divided by the volume displacement rate by the agitator. And often we find that NQ is greater than 1. Why? Just like it's very common to have an NQ which is around say 1.3 or 1.8, right? So how come we are having a flow being generated which is higher than the volume displacement rate? Because of the fact that from the bottom and from the top, in case of turbine, you see that it generates the current, it moves up and again moves downward from the top, and here it diverges, moves from the bottom, gets reflected by the bottom, and here it comes up. So we have an inflow of liquid from the top and the bottom, and because of that this volume flow rate produced by the starter is higher than its volume displacement rate. So because of that we have the flow number higher than flow number higher than unity. So next is the power consumption, which is our prime interest here. So power consumption is generally represented in terms of power number, but that we will discuss later. What is power consumption and how we can calculate that? Power consumption calculation. Right. So power supplied to the fluid is this flow rate. See, the flow rate Q multiplied by rho into V2 square by 2. So this is basically the kinetic energy per unit volume, right? And this is the volume flow rate. So obviously we will have the power supplied to the fluid. From this we can calculate. So V2 square is equal to VR2 square plus VU2 square, right? So VR2, just we have shown that it is equal to this U2 minus VU2 into tan beta 2 whole square plus VU2 square. And again this VU2 is equal to K into U2. So 1 minus K into tan beta 2 square plus K square whole bracket into U2 square. Right. So V2 square is equal to, we can write alpha into U2 square. Right. So this alpha, what I have written, or whatever, it's basically a constant, right? Or let's call it K prime. So K prime into U2 square. So K prime into pi into dA into N whole square, V2 square. So PF, power supplied to the fluid, it's equal to Q Q is basically NQ, the flow number, into N into dA cube into K or into rho into K into pi dA N whole square. So we have the definition of power number, rho N cube dA to the power 5, and here it is NQ into K into pi square, right? NQ into K into pi square, K into, K prime into pi square. So what you can finally write, pi square by 2 is there, so this is 2, this is 2. So power number is some constant alpha into NQ, right? So power number is proportional to the flow number that we can establish from here, and this is the power supplied to the fluid. But this is a very semi-empirical kind of theoretical analysis we are presenting here, but actually there are a lot of non-idealities. It's not only the kinetic energy, there are different other forms of energy. The kinetic energy is being wasted in swirling in this level, in maintaining the level above and over the datum, right? The stratification of the liquid in case of specifically the unbaffled tank. So there are a lot of issues which actually restricts the use of this power number to flow number proportionality. So we have to go by more basic approach of engineering, that's the dimensional analysis, right? So power we will try to relate dimensionally to in a dimensional analysis specifically by using this Buckingham pi theorem and all, right, to the different appropriate parameters and variables of this system. These variables includes the geometric and this rotational speed, then the density, viscosities, etc., the diameter, etc., right. These are gross variables. So actually the power usage calculation is performed by dimensional analysis. Right. So which is that power to be given to that agitator is a function of what? Is definitely a function of RPM, liquid density, liquid viscosity, right. The diameter of this impeller, or diameter of this, what I have used here, diameter of that impeller, acceleration due to gravity, and there are other many geometric factors like h, j, dt, then E, then W, then L, etc., etc. Right. So if we perform a dimensional analysis here by dimensional analysis, we will get the power number P divided by rho into N cube into dA to the power 5. That is, the power number is a function of this group N into dA square into rho divided by mu. We also have N square dA by G, right. N square dA by G, and we have the dimensionless different ratios of these groups like M, right. So these collectively are called shape factors. such as the standard definition S1. How we define it? S1. This you don't have to remember. Like S1 we define as you see dA by dt, the fundamental ratio. S2 is E by dt. S3 is L by dA. S4 is W by dA for turbines specifically. S5 is J by dt, etc. So these are the standard notations we use. Now what are these numbers? This is definitely the Reynolds number. And this is the Froude number. So, and that's the typical power number. So, let's discuss the significance. Reynolds number, NRE, is inertial force by viscous force, and we know that this is rho v L by mu, where v is the characteristic velocity and L is the characteristic dimension. Here NRE is rho, v is pi and dA into dA, the characteristic dimension, divided by mu. So this is, if we drop this pi, it will be n into dA square rho by mu. Now NFR, Froude number, that's the inertial force by gravitational force this is, the inertial force is, here, v square by Lg, v is the characteristic velocity, L is the characteristic dimension again. So this is n into pi into dA whole square divided by dA into g. So it is n square dA divided by g. And power number, what we have already discussed, Np, it is equivalent to the drag coefficient. Right. Because the power number, you see, it is P divided by rho into n cube into dA to the power 5. So it is P divided by pi into dA into n. Right. Power by velocity divided by this n into dA into pi whole square multiplied by dA square. So this is power divided by characteristic velocity, and here velocity square, and this is area, characteristic area, right, into rho. Rho is always present, right? So this is the force, and if we put a half here, so it is rho v square A, so this is equal to the drag coefficient. You see that drag is specifically here is favorable for agitation. If we churn agitator in a tank filled with air, there will be practically no motion being created because the air has got a very low density, right? But if you increase the density, you switch from gas to the liquid, what will happen? Here, whenever we are switching from gas to the liquid, right, the drag will increase, okay? So the drag basically will increase if I am switching from gas to the liquid, and that drag actually helps you to transmit the power from the starter to the fluid, right? But you see that this is the process where drag is favoring this power transmission from the shaft and the impeller to the liquid. Now, the question is that how will you measure finally? This is a dimensional analysis. You have got the relation that power number is a function of Reynolds number, Froude number and the shape factors. But what is the relation? The relation or the how to calculate the power required. That is via experiment and dimensional analysis. Right. And what are the results of that? That we will discuss, and which is general and we can use it for any sort of this analysis. So, this is what we are going to plot, the actual functional trend between the power number and Reynolds number. So, this is NP versus NRE in double logarithmic or log-log plot. So, we have NP, we have NRE, and the plots are something like this. Right. So, this dotted line represents the trend for unbaffled tank, the solid line for baffled tanks. Right. And here is somewhat to have an idea, this is 10 and this is 10 to the power 4, and the curves A, B, C and D. See, this A, B, C and D, these are marked for different shape factors S1, S2, S3, S4 and S5. Just like this, just for the set A, I am giving, this is given in the handout, 0.33, then 0.33 here also, this is 0.25, then 0.2, 0.1 and S6 is 1. Right. So, these are the values for which we get. So, if we generalize this, you see that before this Reynolds number 10, right, we have a linear trend in the log-log plot with a slope of -1. Observation 1, that is for low NRE less than 10, we have same relation, same NP versus NRE relation for both baffled and unbaffled tanks. Right. So, what is the relation? Relation is NP is equal to some constant divided by NRE. Right. That is very, very important. We will solve problem in the next session using this. So, NP, it is P divided by rho into N cube into dA to the power 5, and that is equal to KL divided by NRE. So, which is dA square into N into rho divided by mu. Right. So, this square cancels out with cube, N cancels out with square, rho cancels out. So, it is independent of density, and here from we get that power is equal to KL into mu, right, into this N square into dA cube. Now, on the other hand, for high NRE greater than 10 to the power 4, For unbaffled tank it's different, but in case of baffled tanks, which we use mostly, we have NP constant, right? It's independent of NRE. So power, you can say that here it is dependent on the density, N cube into dA to the power 5. So these relations in the next session we are going to use to solve some of the problems of agitation and mixing. Thank you.